Now, the big idea we talked about last time was one of the most important ideas that comes up in integration. And that's the idea of substitution. Substitution is essentially, it's the sledgehammer tool when it comes to integration. It's the go-to thing that you're going to use more often than anything else. Oftentimes you're going to get so comfortable with it, you might not even think about the fact that you're doing substitution. And the idea of substitution is to say, I want to simplify my integral. It turns out there aren't very many functions we actually know the antiderivative of. In fact, very, very small number. Essentially 8. By the end of the semester, we'll get it up to 10. But that's not very many. So how do you solve the rest? Well, you use algebra, you use trigonometry, but a lot of what you do is you look for substitution. Now, the idea of substitution, just a quick refresher, it's been a while. It's probably good to remind ourselves. It says if I have f of g of x times g prime of x dx, I can rewrite this as the integral f as a new variable u du. Where what's happening? Well, what's happening is that this g of x, that corresponds to our u, and then the derivative of g prime of x times dx corresponds to our du. And really what our goal here is to simplify the expression. If we keep simplifying often enough, we'll get it down to something that's on our short list, or perhaps we'll have some other tool. Now, the big question is, how do you know what to substitute? Because you say, what should u be? That's a good question. The answer is you have to look around. And a lot of this comes with practice, but I'll tell you there's two places to be looking for things. So the big thing to look for is, say, is there a function that's sort of a function inside of a function? So think of I'm looking for something on the inside. And if you see that, that's a really strong candidate. The other thing to look for, if you're like, I'm not so clear about that, is you can ask yourself the question, well, is there something that's a nice derivative? Do I see like, oh, I recognize that as the derivative of something nice? Those are the two places to look. Now, I'm not claiming that will get you everything, but that will often get you a long ways in the process for the types of problems that you're going to be seeing. So here we have this problem. Find the antiderivative, or we could say the integral of 2 divided by, in the denominator, t times 4 plus log of t to the 3/2 power. So, given what we just talked about, what would be a good substitution? Well, of course, before we do that, do we need substitution? Maybe this is one of our 8 functions. No, it's not. 8 is a small number. Okay, so we do need substitution. What should we substitute? Well, look for something on the inside. Well, 4 plus log t is inside this function to the 3/2 power. So that's a pretty good clue. We should try it. Does it mean that's going to work? Not necessarily. Now, the other thing that's going for 4 plus log t is notice that there's this over t part here. And we recall that if we take the derivative of log, we get 1 over t. So in other words, that 1 over t shows up on our list of things after we take a derivative. So that's a really good sign. So we get u is 4 plus log t, and du is 1 over t dt. So what does that tell us? Well, the 1 over t dt, that part, is going to become our du. The 4 plus log t will become our u. What about the 2? Well, the 2 is going to be a 2. So we have 2, the 1 over t dt, that's our du. And the 4 plus log to the 3/2, that's u to the 3/2 power. So that looks already more manageable. See, that's our goal. We substitute to simplify. And then if something is simple enough, we have a chance. Now, we're almost there, but we want to write this in a more convenient, more calculus-y way. Now, you might say, more calculus-y? How could it be more calculus-y? We already have the integral sign. Well, in this case, it's the power. You should think of this as u to the minus 3/2. And the reason you want to write it in that way is you really like to have a u to a power, because that's the rule. You know how to integrate like u to the k. So you want to have it in that format. Now we're ready. This is on our list. not the 2. Don't worry about the 2. The 2 is a constant. Constants come out. But u to a power is the thing that's on our list. So what do we get? Well, we're going to have 2. So now we say add 1 to the exponent. So negative 3/2 plus 1, negative 1/2. Now you need to divide by the exponent. If it's a fraction, it's oftentimes easier to just say multiply by the reciprocal. If you flip negative 1/2 over, you'll get negative 2. And then, of course, because you want full points, if it's an antiderivative, don't forget the plus c. That's very important. All right. So what do we have? Well, are we done? Not quite. The problem is we ended up with u. We started with t. So we really should have our antiderivative be a function of t, not of u. But that's okay. The last step is to substitute back. So 2 times negative 2 makes negative 4. Then we get 4 plus log of t to the negative 1/2. And that is perfectly fine to leave it in that form. All right. So there's our problem. Now, that was what we talked about last time, was substitution. This time, we're going to talk about substitution. Now you might say, well, wait, hold on. How can you talk about the same thing twice? Well, the thing is, there's 2 types of integration problems. See, this type of integration problem is an indefinite integral, which means we're looking for a function. There's another type of integration problem, which are definite integrals. We're looking for a number. Now, here's the thing. It's actually pretty simple. The same principles apply. So you still make the same substitutions. The only thing you have to do is to remember to update all the occurrences of your original variable. Now, what are the ones that you might not think of? Sometimes we say there are hidden ones. So when we talk about our notation here, we say integral from a to b of f of x dx. What we really mean when we say a to b is we really mean to say from our variable x equals a to x equals b. So our bounds are also tied to our variable. So if we introduce a new variable, our bounds have to change to reflect what the new variable is. But that's actually not so bad. It's actually a lot easier than it sounds. So what's happening? So let's look at the very bottom. So if my original integral went from a to b of f of g of x times g prime of x dx. This one, it's really easy to see the substitution. This is set up for u equals g of x. Say, okay, so our substitution down here is our u equals g of x. And we say, all right, let's look at our pieces. Our function transforms to f of u. Our g prime of x dx transforms to du. And then our integral, well, our bounds have to be updated. So what you do is you take your variable and plug it into your function here. So if I have x equals a, u would be g of a. And if I had x equals b, plug it in, u would equal g of b. So that my bounds go from g of a up to g of b. Now, you'll see that it says there are 2 approaches to working with definite integrals. Some people don't like to update the bounds. Those people are silly. You should always update the bounds. It's the far better option. And we'll try to demonstrate why in just a moment. But what they do is they say, look, I'm just going to drop bounds, and I'm not going to worry about it. And then I'm going to do my integral by finding my antiderivative, go back to my original variable, and then I'll evaluate them. The catch with that is it's not always possible to do that. We'll see an example why. On the other hand, the better way is update the bounds as you go. Now here's the beautiful thing. The problem we just did, just a few minutes ago, we said, remember we got down to that function of u and said, okay, now we got to go back to what we started with as a function of t. With definite integrals, you never have to go back. It's always full speed ahead. So you don't have to, once you get the antiderivative part, you never have to say, okay, now let me go back to what my original variable was. No. You just evaluate, you're done. Life is good. Life is good. So essentially today is just, the moral of today is don't forget the bounds. All right. Well, time for some practice. So I said I wanted to show an example of why it's useful to update the bounds as you go. So suppose you have this problem, the integral from -2 to 1 of 2x plus 1 times e to the power x squared plus x cubed. It looks like a harmless integral. How bad could it be? Well, let's find out how bad it could be. So here's sort of the method 2. So if we did method 2, what would we do? Well, method 2 says the following. It says, look, don't worry about the bounds, just find an antiderivative, and then we'll evaluate. So we say, all right, let's look at this integral, this expression. Is there a good substitution to make? X squared plus x. That looks like a really good substitution. Now you might want to say, why x squared plus x? Why not x squared plus x cubed? Well, what's nice about x squared plus x is that the derivative is right there, that 2x plus 1. So because we have that derivative ready to go, x squared plus x is a magical, wonderful substitution to make here. And so we have du is 2x plus 1 times dx, and we're like, wow, this is fantastic. And then we have, it's the integral of e to the u cubed du, and then you're stuck. There isn't a nice antiderivative of e to the u cubed. It can't be done. As much as you'd want to, you can't be done. Now, I know you're very creative, and I say, look, I can channel my inner creativity. I can write a function down. It's not going to be right. I know you're very creative. This is not the time to be creative. Be correct. That's our goal. Now, you're probably thinking, okay, well, fine. All right, it failed in method 2. It's got to fail in method 1. Well, let's actually do it. Okay, so let's go and try the one where we update the bounds as we go. Now, updating the bounds as you go is actually not so hard. See, here we go. We're just going to put our bounds in. We say, okay, I need to update my bounds. So what I do is I take my bound. This is an x bound, because I'm integrating with respect to x. So that says x equals -2. I put -2 in for x into my relationship. -2 squared plus 2, what does that become? It becomes 2. It comes 4 minus 2. So it says that my new lower bound is 2. Put in our upper bound, 1. 1 squared plus 1 is also 2. So our upper bound is 2. Now, here's the thing. Definite integrals have an edge, because there are some definite integrals that you can do where you can't do indefinite integrals. That definite integral you can do. What is it? It's 0. Because the lower bound and the upper bound match. And so you get an integral of 0. See, your original one, it wasn't so clear what to do. But now, once you update, things work out really nicely. So that's why I like to say, update as you go. It'll work out a little bit better. All right, well, let's try some more examples. Find the integral from 0 to pi fourths of secant squared theta tangent theta, d theta, by first making the substitution u equals tangent theta, and then making the substitution u equals secant theta. Okay, so we get to do this problem twice. So let's just follow the instructions. So let's start with the tangent theta. So let's say, all right, if u equals tangent theta, what would du become? Secant squared. And so we look up here. Oh, I should also have a d theta here. We look up here and we say, hey, secant squared d theta, that's good. That will become the du part. Tangent of theta is also good. That becomes the u. So what we get is that this integral will become a u du. But we're not done because we need the bounds. So we put it in our bounds. All right, tangent of 0 is 0. Tangent of pi over 4 is 1. Now we have an integral we can do. So let's do the integral. Integral of u du, what will that be? U squared over 2. Or if you like, add 1 to the exponent. So that would be 2, the exponent, divided by the exponent, 1/2. Remember, when we're doing definite integrals, you don't need a plus c, because we're going to do the evaluation, so the plus c makes no difference. Now we're going to evaluate this from 0 to 1. If we plugged in 1, well, we get 1/2 times 1, which is 1/2. If we plugged in 0, we get 1/2 times 0, which is 0. So our final answer is 1/2. All right. Now that's if we make that substitution for u equals tangent of theta. It said to do it twice. All right, so let's do it another way. So the second round says, let's try secant. So u equals secant of theta. What's the derivative of secant? Secant tangent. Secant theta, tangent theta, and we have a d theta on the end. So if you look up in our original integral, we might say, well, we don't really have a secant theta tangent theta. Well, we kind of do. It's just written in a weird way. See, the secant squared theta tangent theta could also have been rewritten as secant theta times secant theta tangent theta. Now we say, oh, that's not so bad. We say the first secant theta, that could be our u. The rest of it goes into our du. So this again becomes the integral of u du. You're like, okay, no big surprises. But what about our bounds? Let's plug in. When you plug 0 into secant, what do you get? Secant of 0 is 1. That's a little different. When you plug in pi over 4 into secant, okay, now that one might test you a little bit. Secant of pi over 4? Square root of 2. Square root of 2. That's the right answer. So, in case you're wondering how do you get that, cosine of pi over 4, you can write that as 1 over square root of 2. And to get from cosine to secant, you flip. So that's how you get to square root of 2. Now you might say, these are not the same integral. Well, we're not claiming that they're the same integral. Our goal is to get the answer. Let's see if the answers are the same. It's the same antiderivative at least. So it's 1/2 u squared. Evaluate that from 1 to root 2. Don't have enough space. I'll move down here. 1/2 times square root of 2 squared. Well, that's 1/2 times 2, which is 1. Subtract 1/2 times 1 squared. So this becomes 1 minus 1/2, which is 1/2. Now we're like, whoa, it's the same answer. So it's not that surprising. And it should be the same answer because it shouldn't matter. But I want to point out a couple of things. It is possible to have multiple different substitutions. And there's not like always one right substitution. The right substitution is always the one that makes things easier, so it is possible to have more than one right one. And yes, you should always get the same answer. It shouldn't matter what you substitute. All right, well, let's try another one. An example. Find the integral from 0 to 1 of square root of y over y cubed plus 1. Well, not so clear. Not so clear. So we start thinking to ourselves, where are places that we can look for a substitution? Well, is there a function on the inside? Y? No, that's not going to help you. I mean, I can just change the name. That's not going to do anything. Y cubed plus 1, that's kind of on the inside. That's in the denominator. But then the derivative of y cubed would be 3y squared. I don't have anything like that. But remember we said there were two places to look. You don't just have to look for a function on the inside. Where's the other thing you can look for? Something where it shows up as a derivative. Now, y cubed plus 1 in the denominator, that doesn't show up as the derivative. But square root of y can. That's like y to the half. Can we think of a function where when we take the derivative, we get something that looks like y to the half? What would that be? Not quite cube root of y, but there is something about a 3. y to the 3 halves. Y to the 3 halves. So if you take the derivative of y to the 3 halves, I'm not worried about the numbers, the constants. So the 3 halves coming down, I'm not going to worry about that. But when you take y to the 3 halves, the new exponent is 1/2. So we say, hey, let's try to guess that this is telling us what our derivative of our substitution should be. And if we go off of that, and it's a good thing to try, that says, try something that looks like y to the 3 halves. And now we're like, oh, you know what? We probably could have guessed that before. What do you notice about your denominator? What does it look like? What's another way to think of y cubed? Take y to the 3 halves squared. So what would you get downstairs now under this substitution? This part would go to u squared plus 1. Now u squared plus 1, that's not just any function when you're trying to find antiderivatives. That's an awesome function when you're trying to find antiderivatives. So one of the things you're looking for is you're saying, look, I know the 8 functions I know how to find the antiderivatives of. I should be thinking about those functions when I'm thinking of substitutions. So we say to ourselves, okay, let's figure this out. Our du would be 3 halves y to the 1/2 dy. Well, I've got that square root of y dy. That's good. The 3 halves here, not so good. But through fancy technology called multiplying both sides by 2/3, we get that 2/3 du is y to the 1/2 dy. So constants are easy to move around. Variables can also be moved around, but you got to remember to update them. So you don't want to do too much of that. But moving constants around, piece of cake. So what do we get? Well, let's update everything. So you're going to rewrite the integral we started with. So we had the square root of y over y cubed plus 1 dy. All right, so there's 3 pieces. So the 3 pieces are, remember, you got to get something to account for the dy. So that's going to be this part. The square root of y dy, that'll become our du. You also then have to say, okay, everything else has to be rewritten in terms of your new variable. So that everything else is the y cubed plus 1. That's going to become u squared plus 1. But we don't stop there. Oh, whoops. You're right. I forgot my constants. There should be a 2/3. All right. There's one other thing we have to do, which is the bounds. You got to update the bounds. See, these bounds here, 0 to 1, those bounds are attached to y. It's y equals 0 to y equals 1. We're not dealing with y anymore. We're moving to u. We have new bounds. We have u bounds. We're no longer going from y equals 0 to y equals 1. We're no longer 0 to 1. We're now going to go from 0 to 1. Now you're probably thinking, what? What was that speech for? So be careful here, because oftentimes you see examples like this and said, oh, they didn't change the bounds. We did actually change the bounds. It's just sometimes by coincidence things line up. Now, how did we change it? Well, you plug in 0. 0 to the 3 halves is 0. So that's why we still stayed at 0. And 1 to the 3 halves is still 1. So we did actually change our bounds. They just happen to look the same. All right, so now we're ready to finish this off, because lo and behold, 1 over u squared plus 1, that is one of our things we know the antiderivative for. I hope you know it. It's a beautiful thing. If you don't, take Calc 2, then you really get to know it. It's arctangent. So we're almost done. So what's left to finish? Well, we've got to evaluate. So we have 2/3 arctangent of 1, subtract 2/3 arctangent of 0. Arctangent of 0? Do you know that one? Arctangent of 0 is 0. That goes away. How about arctangent of 1? Do you know that one? Pi over 4. So the arctangent of 1 is the angle where the tangent of that angle gets you 1. And that's 45 degrees, or in our calculus terminology, pi over 4, which we can simplify our final answer to be pi over 6. And that's it. All right. Well, let's do another one. You're probably going to see a theme. We're going to just keep saying, let's do another one. Now, this one is fun because I'll be honest with you. If I saw this without a hint, I don't know if I could do it. I'm pretty sure your recitation instructors would also have a hard time doing this one. But we have a hint. This looks like an integral which is crazy. It's the integral 0 to pi halves sine of x to the power cosine of x over sine of x to the power cosine x plus cosine of x to the power sine of x. That's weird. What were they thinking when they put this function together? And how do we find it? Now, I will tell you how you do not find this problem. You do not find it by finding an antiderivative. It's not going to happen. Now, you might think, I thought all of integrals were solved by antiderivatives. And that's not true. Integration actually existed thousands of years before differentiation. This idea of breaking things into parts and adding them up is ancient. It goes back to the Greeks. And so you can do integration without differentiation. So don't feel like you always have to find antiderivatives. Now, that being said, on the exam, yes, look for antiderivatives. But I just want you to be aware there are other things that can be done. So we're trying to find this integral, and it says, let's make a substitution. So we're just going to follow the hint. So let's just follow the hint and see where it takes us. So here's the substitution. What would du be?
1. -1.
Negative 1 times dx. All right, so that's pretty simple. So this will become the integral. Let's do our bounds while we're here. What will our lower bound become? So this is an x bound, because it's a dx. What will be our lower bound here? Pi halves. What will be our upper bound? 0. That's weird. Well, we'll get to that in a second. All right, then we have what? Well, we have sine of pi halves minus x to the power, not pi halves minus x. X equals pi halves minus u. My apologies. Pi halves minus u, cosine of pi halves minus u, divided by... See, the hard part about this problem is just writing everything down. And, well, maybe that's not the only hard part about this problem. But if you, everywhere you see an x, you replace it by pi halves minus u, and you just very patiently work your way through, and lo and behold, the minus dx becomes a minus 1 times du. Now, we don't like the bounds being out of order. We always like to go from low number to high number. If I want to switch it from 0 to pi halves, what do I need to do? Whenever I change the order, essentially it's an orientation change. Any orientation change, flip the sign. But hey, we already have a minus. So we can just put the bounds as 0 to pi halves, and then we get rid of this minus here. So that's good news. Now we have all these other really crazy looking functions. Sine of pi halves minus u, cosine of pi halves minus u. Now pi halves minus u versus just u, if we think of these in terms of angles, they're not just any kind of angles. There's a specific term for these. Do you know what they're called? So like, as an example, like 20 degrees versus 70 degrees would be if we used degrees. Or 10 degrees versus 80 degrees. Do you remember what those are? Complementary. They're complementary angles. And if you remember something about sine and cosine, one of the things that's true is that if I take the sine of the complementary angle, it's the same as the cosine of the angle, and vice versa. Essentially, you can think of that's where the co is coming from. It's like of the complementary angle. So what does that allow us to say? Well, that says that this sine of pi halves minus u is really just cosine of u. And this exponent, cosine pi halves minus u, is sine of u. And do the same thing downstairs. So cosine of u, sine of u, and then plus sine of u, cosine of u, du. All right. So far, so good. Now at this point, it's still not clear that we've done much, but we've actually done the hard part. So here's the magic. These two integrals are the same, because all we did was we did a transformation. We did a u equals pi halves minus x. We worked out what would happen, and that's what we ended up with. So they have to be the same value. Let's give that value a number here. We'll call it A for answer. All right? So I'm going to figure out what is 2A. So how am I going to do 2A? Well, the thing is, I'm just going to add these integrals together. And you're probably thinking, Steve, that's a terrible idea. This has in terms of u, and that's in terms of x. And you're right, that is a terrible idea. So we're just going to put u's here. And now it's a great idea, because everything's in terms of u. Because I can just change the name. It doesn't matter. It goes away. So let's add these two together. Now, compare the denominators. What do you see? They're the same denominator. So when I add these two together, I just need to add the numerators over the same denominator. So I have cosine u to the sine u, and sine u to the cosine u. That's my denominator. From the first integral, that would be sine of u to the power of cosine of u. From the second, that would be cosine of u to the sine of u. What do you see about that? Takes a second to see it. It's 1. Now, can we integrate 1? Yes. Yes, 1 is something you can integrate. So, what do we end up with? We end up with u from 0 to pi halves, which is pi halves. Now remember, that's not our answer. That's twice our answer. So what's our answer? Yeah, so our answer is pi over 4. So that's the value of the original integral. So here, you could not find the antiderivative, but because of, essentially what happens is there's a little bit of symmetry that's hidden inside of it, and we can exploit that. So there's advantages to doing definite integrals. Some things you can't do with indefinite integrals, you can do with definite integrals. All right, another example. Find the integral from 0 to pi fourths, 2 minus secant squared theta to the 1/2 secant squared theta d theta. I like this problem. This is a good problem. Now, this is not on our list of 8, and that's okay. Because if it was on the list of 8, it'd be boring. We're like, all right, we want to challenge ourselves. So, do we see a substitution? Now, you might say, okay, 2 minus secant squared. Well, the derivative of 2 minus secant squared would be negative 2 secant squared theta tangent theta. Close, but not what we have on the outside. But it was really close. I'll give you a hint. This problem is basically saying, or maybe it's trying to whisper to you. You know, we're young. We're just barely learning to hear it. But it's trying to whisper to you, make a certain substitution. And you're probably like, which one? Which substitution should I make? And it says, look at me. Look at me. It says secant squared theta d theta. What gets us a derivative that looks like secant squared? Tangent. It's practically begging you, please substitute tangent, because when you see a secant squared, it's like, that should be a tangent. Okay, so we know what we need to substitute. We need to substitute tangent. Now you're probably thinking, that's a bad idea, Steve. Well, probably. But at least if we substitute tangent, this part is great. So let's at least make a note here. Now, why is it a bad idea? Well, the reason it's a bad idea is where's the tangent? There's no tangent in the rest of it. Or is there? What do you know about secant squared? Is there, let's say, an identity that involves secant squared? You're probably thinking, yes, there's many identities that involve secant squared. is there a useful identity that involves secant squared and tangent? Because remember, we want to write everything in terms of tangent. Is there an identity? Someone said yes. Do you remember what the identity is? So secant squared is equal to 1 plus tangent squared. That's the identity. Brought to you by the makers of cosine squared plus sine squared equals 1. Because it really is the same identity. It's cosine squared plus sine squared equals 1. Divide everything by cosine squared. That's what you get. Now, how do we use it? Well, what we do is we say, look, if I have trig and I need to rewrite it, use an identity. So this is 0 to pi over 4 of 2 minus 1 plus tangent squared theta to the 1/2 times secant squared theta d theta. Now, I haven't done a substitution here. What I'm doing is I'm rewriting it using trigonometry, which is one of our tools. You essentially have 3 tools for antiderivatives. There's the, is it one of my basic 8 things? Do I have algebra or trig, or do I have substitution? And you just keep going at those 3 over and over and over again, because those are the ones that will carry you through. Now we're okay. Now we can make our substitution. So let's go ahead and do our substitution. So, first off on the inside, you can simplify this. 2 minus 1 would become 1 minus tangent squared becomes what? U squared. To the 1/2. Secant squared theta, d theta, becomes du. And now the bounds. Okay, so let's update our bounds. Theta equals 0. Tangent of theta will be 0. U equals pi over 4. Sorry, theta equals pi over 4. U will be 1. Tangent of pi over 4 is 1. All right, at least it looks nicer. 0 to 1 of 1 minus u squared to the 1/2. Now, is that something we know the antiderivative for? In other words, is that on our list of 8? No. Can you find an antiderivative of this? In Calc 2, you can, but not now. So you're probably thinking, why have you done this to us? We won't know the answer. But we will know the answer because we have tools. Now, what's our tool? I have misled you here. There is a distraction. I put a 1/2. What if I had put a square root? And now you're thinking, doesn't do anything. Still the same thing. Somebody said something. That's a curve that you might recognize. Do you remember what that curve is? That's a circle. So, if you sketch this curve, square root of 1 minus u squared, it's the top half of a circle of radius 1. This integral, we can think of integrals, one of the ways you can think of integrals is finding the total of an area. So it's like finding the total area between 0 and 1 of the unit circle. So I don't know what the antiderivative is, but I happen to know the area of a unit circle. So the area of a unit circle is pi r squared, so it would be pi, but I don't need the whole area. How much do I need? 1/4 of it. So the answer is pi over 4. And now we're done. So again, this is something that, because it's a definite integral, we have the ability to give an interpretation to it and say, oh, because I understand what this represents, now I can evaluate. And I can get an answer.
If we didn't know that was a circle?
If you didn't know if it was a circle, oh, good luck. Good luck. Well, that's why you came today. Now you know. And knowing is half the battle. So you should be suspicious when you see a square root of something minus something. You should say, sounds like a circle to me. Maybe. Maybe.
Can it vary sometimes, be more than pi, a fourth of a circle?
It can be more than 1/4 of a circle. Yeah, sure you can. You can make things very interesting, as you will see on the quiz. Okay. But that's for the quiz. Let's finish up with one more example. Our last example of the day. Find the integral from 1/2 to 1 of r of 4x dx, given the following information. We have the integral from 1 to 3 of r of 2x, that's 5. Integral from 1 to 2 of r of 3x is 4. Going from 4 to 3 of r of x, well, that's weird, 4 to 3. Well, okay, we'll roll with it. That's 2. And 0 to 1 r of 5x is 6. So at first glance, it seems to be like, what? How do these things all relate together? How can I figure things out? So the problem is that the reason it doesn't feel like things necessarily, you have the information you need, is you have like the insides aren't the same. On some of them you get like a 2x, on some you get like a 5x, over there it's a 4x. You'd really like these to be more consistent. So let's change everything. Let's make them all the same, so that I really can do more apples to apples type comparison. So I'm going to go through and update them. Now this one, I kind of like the way it is, the r of x dx. I can make a really easy substitution called x equals u, and then I get dx equals du. So this becomes the integral of r of u du. Now the thing I don't like about that, by the way, this is just a way of saying you can just change the variable name to be whatever you want. It doesn't do anything. But what we don't like about this one is the bounds. 4 to 3, not cool, man. We want to go from low number to high number. So let's switch it from 3 to 4. If we do that, what happens? It becomes negative. All right, let's try to update these others really quickly. Let's do this one. R of 2x, let's set u equal 2x. So du would be 2 dx. I'll move the 2 across. So this becomes the integral. Then I have an r of u. The dx will put a 1/2 du. But now I got to get the bounds. They were for 1 to 3. What should they be? So put 1 in. You get 2. Put 3 in. You get 6. So we get the integral from 2 to 6 of r of u du is 10. Okay, well that's feeling a little bit better. Let's do some more here. Switch color so we don't get too confused. U equals 3x. Du is 3 dx. Again, I'll divide by the 3. So we get the following. This is the integral. So we'll have r of u. Then the dx becomes a 1/3 du. What will our new bounds be? 3 to 6. So we get that the integral from 3 to 6 of r of u du is 12. All right, this one on the end. That one shouldn't be so bad. U equals 5x, du equals 5 dx, divide by the 5. We get the integral of r of u times a 1/5 du. That's 6. What will the bounds be? 5, 0. Yep, 0 to up to 5. So we get that the integral from 0 to 5 of r of u du is 30. So now we have all the pieces of information in sort of a more compatible format. All the functions look the same. They all look like r of u. And so because they look the same, we're able to sort of merge these integrals together as appropriate. Now the question is, what's appropriate? So let's think about the integral we're looking for. So let's do our substitution on our last integral. So here, we would say, let's let u equal 4x. What would du be? 4 dx, or 1/4 du equals dx. So that says our answer is going to be 1/4 the integral of r of u du, where the bounds will be from 2 up to 4. So I need to find some way to put these together to go from 2 to 4. And now we start saying, hey, there's a 2 here. That's a promising sign. So I'm going to go 2 up to 6. of r of u du. But the thing is, that's not 4. True fact. 6 is not 4. All right, so we say, okay, where's the 6? Is there a 6 anywhere? There's a 6. So what I'm going to do, this will look a little bit strange, but I want to add 6 to 3. Now the reason I'm going to say it looks a little bit strange is that's not the integral there. Why did you flip? Well, I flipped because I just wanted to have that upper bound match that lower bound. I wanted those to match up. Because if I put those two integrals together, what do I end up with now? 2 to 3. Because if these match, I'll go from 2 to 3. Okay, do I have a 3 somewhere? I have a 3 right there. So 3 up to 4 of r of u du. And again, the key here is that the bounds are matching. So what we have is that this is the integral from 2 to 4. Well, what's the first one? 10. What's the second one? Negative 12. Negative because we have to flip the bounds. So minus 12. What's the last one? Negative 2. Which tells us we end up with negative 4. So our answer is 1/4 of negative 4. So that integral is negative 1. Ah, good. That's it. We're done for today. Thank you for being here.